Hello all, welcome back. So, in the previous lecture we have completed all the topics related to subsurface water, which I was planning to complete within this course on engineering hydrology. Now, let me summarize the third module, that is the subsurface water. Subsurface water, in the beginning itself I have explained that we are discussing about the water which is present beneath the ground surface. Beneath the ground surface itself, when we discuss, we are having two different zones. One is unsaturated zone and the other one is the saturated zone. There is a clear boundary which is differentiating between the unsaturated zone and the saturated zone, that is the groundwater table. Below the groundwater table we are having the saturated zone and above that we are having the unsaturated zone. And in this course we were discussing about the water present in the unsaturated zone, that is related to the process infiltration. So, below the water table, the porous medium is the medium through which the flow is taking place. The flow which is taking place through the soil or rock strata, that is termed as the porous medium. So, the porous medium is saturated below the water table, that is all the pores are filled with water, and then above the water table the porous medium is unsaturated. If we consider an unsaturated soil sample, within the soil sample, in addition to soil, there are so many voids present within the soil sample. These voids can be filled up by water or by means of air. If the voids present in the soil is fully filled with water, then we will be calling it as saturated soil. And if it is partially filled with water, that is some of the voids are filled with air, then we will be calling it as unsaturated soil. Sometimes all the pores will be filled with air only, there will not be water present, then we will be calling it as the soil is in the dry state. And after understanding this, we need to have proper understanding related to pore space which is present in the soil. So, in the case of a completely dry soil, we are having zero moisture content, or if you are talking about relatively dry soil, there will be some amount of moisture content present depending on the initial condition. So, there will be a minimum value of theta. Theta is the representation used for representing the volumetric moisture content. And in the case of soil which is having maximum value, maximum soil moisture content, that is equivalent to the porosity of the soil. So, completely dry soil will be having theta is equal to 0 and saturated soil theta is equal to eta. So, this soil moisture content can vary between 0 to eta. After seeing the pore space, we have moved on to the wetting process. Relatively dry soil we have considered, that is how the wetting takes place within the subsurface. So, in the case of relatively dry condition, there will be only adsorbed water. Adsorbed water will be present in the soil in the dry state. So, in this case, due to the electrostatic forces between the water molecules and soil particles, there will be adsorbed water present in the soil. So, the main reason behind this adsorbed water is the electrostatic force between the soil particles and the water molecules. Rainfall or infiltration may be due to some agricultural activities is taking place in the soil, then the wetting progresses. The process of wetting will be progressing and more water is available, that time the capillary forces become predominant. So, when the dry state, relatively dry state is becoming wet, some water is getting infiltrated or some wetting process is taking place, the capillary forces will come into picture, that is the suction forces. After that, again and again continuous wetting is taking place, all the pores will be filled with water and it will be progressing towards saturation. So, when all the pores are getting filled up, initially it was relatively dry, then electrostatic forces were predominant, then some more water is added, then capillary forces coming into action. After that, the flow of water is continuing, wetting process is continuing. At that time, we will be having saturation and gravity force will be predominant. Now, after understanding the pore space and wetting process which is taking place within the subsurface, we have moved on to the driving energy for flow through porous media. So, the total energy was represented by H. It was consisting of 3 components in the unsaturated region, given by H is equal to psi plus Z plus V square by 2G. In the psi was representing the suction head, Z datum head and V square by 2G the corresponding velocity head. So, we have found that the velocity head compared to the value of psi and Z, that is the datum head and the suction head, the velocity with which the flow is taking place through the soil is very small. So, velocity head will be very small and that can be neglected. So, in total, if we talk about the total head causing the flow within the unsaturated region, we can write the expression as sum of psi and Z, that is sum of suction head and the datum head. So, the energy causing the flow of water in unsaturated medium is the sum of 2 components, those are sum of suction head and datum head. So, H can be represented as psi plus Z. After understanding the driving energy which is taking place within the unsaturated zone, we have moved on to the derivation of the unsteady unsaturated flow equation. One dimensional unsteady unsaturated flow equation was derived. It was consisting of our fundamental equations related to continuity equation and the momentum equation, that is the mass and momentum conservation equations together considered to develop the one dimensional unsteady flow equation in the unsaturated zone. So, continuity equation was given by this partial differential equation, and momentum equation we have considered the Darcy's law and it was given by Q is equal to KSF. And after that, corresponding to SF slope, we have made use of the energy causing the flow and substituted for that particular term SF, and finally combined together the continuity and momentum equation combined together, and finally the equation of momentum was found out to be in this form, which was having the term soil water diffusivity, soil moisture content and also hydraulic conductivity. In this case, continuity equation we were having the terms related to Darcy's flux and the soil moisture content. So, from this equation, from the momentum equation, Q has been substituted in the continuity equation and then derived the final form of the 1D unsteady flow equation. So, unsteady flow equation is nothing but the commonly known as the famous Richard's equation that is given by this particular equation. So, this is the equation representing the flow through unsaturated zone, which is unsteady flow equation in the unsaturated zone. And after that, we have moved to the hydrologic process which is known as infiltration, which is the process in which the water is getting infiltrated into the ground from the ground surface. This process in detail we have understood, and for understanding that we have studied the soil moisture profile. So, as the water moves down, it wets the soil, and near surface, that is water is getting infiltrated into the ground. So, as time passes, the near surface soil will become saturated or it may approach saturation. That is, as the rainfall is continuously happening or we are watering the agricultural land, at that time the surface soil becoming saturation will be having theta is equal to eta at the ground surface, and this is termed as the saturated zone. So, what we are assuming that the near surface soil will be in the saturated condition at the time of infiltration. not at the beginning, after some time. So, for understanding the infiltration process, we have gone through the soil moisture profile. Soil moisture profile was having the schematic representation as shown in the figure. So, soil moisture we have put on the x axis and soil depth on the y axis, and we have found that it can be divided into 4 different zones. At the top we are having the saturation zone, just beneath that we are having a transition zone which is separating the saturated zone and the unsaturated zone. And within the unsaturated zone itself, 3 ways it has been divided, that is the 2 ways, that is transition is the one which is changing from saturated to unsaturated. And below the transition zone we were having transmission zone and wetting zone, and we have seen an important terminology known as wetting front, that is the clear boundary which is separating the 2 regions before wetting and after wetting. So, within the wetting front we have found a sharp boundary which is having a soil moisture variation, too much of variation. After that we have seen how the infiltration can be represented. We were representing infiltration by means of 2 terminologies, infiltration rate and cumulative infiltration. As we were discussing about the rainfall, infiltration also, one in terms of cumulative depth and the other in terms of depth divided by time. So, infiltration rate is representing the rate with which the water is getting infiltrating, and cumulative infiltration is the water accumulated over time. How much is the infiltration taking place within a particular interval of time. We are not considering the interval, total time and total water which is getting infiltrated, we are considering in the case of cumulative infiltration. After that we have seen the relationship between infiltration rate and cumulative infiltration. Relationship is given by f of t, capital F of t is given by integral of f of t dt within the limit 0 to t. So, how much is the time elapsed between the beginning to end? Within that limits, if we integrate the infiltration rate curve, then we will get the cumulative infiltration. Or if we are having the cumulative infiltration with us, we can differentiate that to get the infiltration rate. Then we have found out how this infiltration is taking place, either via watering or by means of rainfall. So, we can find out certain relationship between infiltration rate and rainfall intensity. While explaining these things, I would like to add one thing. As in the case of evapotranspiration, here also we have seen different terminologies, actual infiltration and also potential infiltration. Potential infiltration is the infiltration which is taking place when sufficient amount of water is there to infiltrate, and actual infiltration is the one which is taking place actually in the field. So, while comparing infiltration rate and rainfall intensity, if the rainfall is occurring at a rate which is higher than what the soil can absorb, the infiltration will be at maximum rate, that is actual infiltration will be equal to potential infiltration. The rainfall is having higher value than that of the infiltration rate. So, we are having sufficient amount of water present there. So, if sufficient amount of water is present, the infiltration taking place will be the potential infiltration. And in some cases, if the rainfall is falling at a rate which is lesser than the maximum soil can absorb or maximum infiltration can take place at that particular location is more compared to the rainfall intensity. Then what will happen? Whatever rainfall is falling, completely it will be infiltrated into the ground. So, the actual infiltration will be less than that of the potential infiltration, but actual infiltration can be equated to intensity of rainfall. So, that is what is written over here, actual infiltration is equal to rainfall intensity in this case. So, there are two cases, one is rainfall intensity is more than that of the infiltration capacity, another is I is less than that of the infiltration capacity. So, if I is less than that of the infiltration capacity, entire rainfall will be infiltrated into the ground. So, that is at that time F can be equated to intensity of rainfall, that is the actual infiltration, it is less than potential infiltration. On the other hand, if the rainfall intensity is more than that of the maximum capacity, maximum infiltration rate, then we will be having potential infiltration taking place. Actual infiltration can be equated to potential infiltration. After that, we have moved on to the measurement of infiltration. Measurement of infiltration is also very important because it is an important factor when we talk about losses from rainfall. That is, we have seen two different approaches for measurement of infiltration. One was head based approach and second one was flux based approach. So, in the head based approach, we were providing certain head of water and based on that the measurements have been carried out. In the flux based approach, we have provided certain intensity or flux corresponding to for infiltration to take place, but we have not gone deep into flux based approach. We were giving importance to commonly used head based approaches based on the infiltrometers. And the double ring infiltrometer in detail we have seen. We have started with single ring infiltrometer and then we have moved on to double ring infiltrometer. After understanding the disadvantages of single ring infiltrometer, we have gone to double ring infiltrometer and we have seen how infiltration can be represented in curves by means of infiltration rate and cumulative infiltration depth. Cumulative infiltration depth curve was an increasing curve as in the case of mass curve, and infiltration rate curve was a decreasing curve. Empirical equation, and then we have seen the theoretical equation. So, empirical equation, three different equations which we have seen are Kostyakov equation, Horton's equation and Walton equation. When you go through the different journal papers, you can see different methods. So many methods are available, but important methods which are explained in the textbooks we have covered over here. After that, we have moved to theoretical equations. Theoretical equations which are derived based on the fundamental laws, that is the mass conservation and momentum conservation principles. Those two equations which we have seen were Greenamt equation and Phillips equation. So, in detail all these we have seen. After that, we have solved some of the numerical examples, and once completing Greenamt equation, we have understood a concept termed as ponding time. By making use of the Greenamt equation, we have found out an expression for ponding time. So, potential infiltration is the one I have already told you. Sufficient amount of water was available for infiltration, and for that we need to have, whenever we are having an rainfall, initially there will not be any ponding taking place. That is, initially whatever rainfall is occurring, that will be infiltrating into the ground. At that time, it is not the potential infiltration. When sufficient quantity of water is not available, the actual infiltration will be less than that of the potential infiltration. Majority of the equations are giving the potential infiltration values, that is sufficient amount of water is available for infiltration to take place. So, there we have explained the concept of ponding time. Time elapsed between the time at which rainfall begins and the time water begins to ponding on the soil surface. That in between time is considered as the ponding time. So, when we are talking about potential infiltration, we are considering already ponding has taken place or sufficient amount of water is there for to infiltrate. So, if we want to calculate the infiltration which has taken place after ponding has taken place, so for that we need to have some understanding of ponding time. So, before ponding, what we are assuming, F is equal to intensity of rainfall, whatever rain is falling is infiltrated into the ground. And after ponding, infiltration will be potential infiltration, F is equal to Fp. After ponding has occurred means there is sufficient amount of water available and then the infiltration process is continuing. Before ponding means rainfall is occurring or watering is taking place, entire water is getting infiltrated into the ground. So, based on the ponding time, we can find out how much is the infiltration taken place after ponding has occurred. So, it is very important to determine the ponding time to determine the infiltration after ponding has occurred. So, for that we have made use of Greenamt equation, that is the contribution is by Main and Larsen, and they have made use of the Greenamt equation. The equation is based on the Greenamt equation, which is derived as a combination of continuity and momentum equation. That particular equation is used and three principles were considered, that is when time is less than ponding time, entire water is infiltrated, and potential infiltration rate is a function of cumulative infiltration, that we have seen in the case of infiltration rate and cumulative infiltration expression given by Greenamt. In that case, cumulative infiltration or the infiltration rate or the potential infiltration is a function of cumulative infiltration. Small f was a function of capital F, and ponding occurs when potential infiltration is less than rainfall intensity, that is F is less than I. F is less than I means intensity of rainfall is more. So, infiltration is at a potential condition. So, at time t is equal to Tp, ponding time what we are telling, we can assume that F is equal to I, infiltration rate is equal to intensity of rainfall I, and cumulative infiltration can be calculated how much of the water is infiltrated, total amount of water infiltrated can be computed by multiplying the intensity of rainfall with the ponding time. So, with that conditions we have derived the expression for ponding time. After that we have made use of the expression from Greenamt equation and found out the expression for ponding time. It is given by this simple equation. So, infiltration after ponding was calculated by finding out the difference between F minus Fp. Fp can be obtained by using ITP and capital F by using the cumulative infiltration expression given by Greenamt equation can be considered. So, capital F minus Fp will be giving you the infiltration taken place after ponding has occurred. So, that is given by this particular expression. So, this equation has to be solved by means of iterative methods, because it is an implicit equation in infiltration on both the sides. So, some trial and error techniques need to be utilized for solving this equation, and after that we have solved some of the numerical examples for finding out the solution of these things, and entire concepts related to hydrologic processes which is taking place, that is infiltration, which is taking place beneath the ground surface. From the ground surface water is moving into the ground. So, that process is infiltration. So, all the technical details about this hydrologic process named infiltration we have covered under the topic of subsurface water. Again I am repeating that we haven't looked into groundwater hydrology. Groundwater hydrology is beyond the scope of this course. So, we have considered, when we talk about subsurface water, we have considered the water which is present in the unsaturated zone or the vadose zone. That much we have covered under the topic of subsurface water. Here I am winding up the module 3 on subsurface water. Thank you very much.